People do all sorts of work where security is important. And among these are transactional operations like bank transfers, cryptocurrency transactions, and also non-financial operations like deleting backups or modifying DNS records. How can such transactions be performed securely? One common solution to this problem is what we call agent applications running on the smartphone. So you can have an app for Bitcoin, an app for Ethereum, an app for your bank, and so on. Unfortunately, the smartphone suffers from isolation bugs. It has a history of jailbreaks due to bugs in the operating system or elsewhere in the stack. And so the operating system cannot guarantee strong isolation for these agent applications. Another solution to this problem is a device called a hardware wallet, which is popular with users of cryptocurrencies. This device has a screen and buttons, so the user can see a transaction and confirm it by pressing the button on the device. Like smartphones, hardware wallets support running many different agent applications. So for example, the Ledger wallet, one of the most popular hardware wallets out there, has over 50 third-party agents in its app store. And these agent applications need to be isolated from each other when running on the hardware wallet, because the user might be tricked into installing and running a buggy or malicious agent. And we wouldn't want, for example, a malicious agent to be able to steal, say, the user's Bitcoin if it's accidentally run on their hardware wallet. Unfortunately, existing hardware wallets also have isolation bugs. They have reasonably complicated operating systems that multiplex applications on top of shared hardware, much like traditional operating systems. And there have been over 10 operating system bugs found in 2 of the most popular hardware wallets out there today. We could also be worried about potential hardware bugs in these designs. Any shared hardware state could be used to infer information about other applications. Like this is what's going on in attacks like Spectre, for example. And so we asked the question, can we build a more secure hardware wallet? Towards this goal, we contribute Notary, a new design and implementation of a hardware wallet. So Notary isolates agents using a technique we call reset-based task switching, and this relies on a formally verified primitive that we call deterministic start. We also have a physical prototype of a hardware wallet that implements these ideas, and we also have some agent applications that run on top of our prototype. Notary's threat model is similar to that of existing hardware wallets. So in this talk, we focus on defending against buggy or malicious agents that may try to break isolation and steal other agents' secrets. And in our work, physical attacks are out of scope, but the ideas we present could be combined with standard tamper-proof hardware that's already used in many existing devices. So to achieve isolation between agents, Notary uses this architecture that has 2 systems on a chip, each with its own CPU, RAM, and ROM. You can basically think of these like they're 2 separate computers that are connected over a really simple interface. On one side, we have the kernel chip, which is responsible for managing persistent storage and switching between different applications that run on the device. But one really important thing about this chip is that we never run any third-party code on here. Now, on the other side, we have the agent chip, and this is where agent applications run one at a time on the device. So this is the chip that runs the third-party code, and it's connected to USB so it can communicate with the outside world, and it's connected to the user I/O path so it can interact with the display and also receive input via the buttons on the device. One important thing about this chip is that it has no persistent storage. Now, these 2 chips are physically separated, and they're only connected by a couple of wires. So there's a bidirectional UART that connects the kernel chip and the agent chip, and they talk over a really simple protocol. And then also the kernel chip has the ability to reset the agent chip. Now, to see how this design provides isolation between different agents, we can walk through an example of how an agent starts up and runs in this architecture. So the first step is that the kernel chip resets the agent chip. So it asserts the reset line, and this has the effect of clearing all the state on this chip. Then after that, the kernel reads the particular agent's code and data, which lives in persistent storage, and the kernel sends this over the UART. So then on the other side of the UART, the agent chip is listening for this code and data, and it downloads this stuff into RAM and then executes it from there. So at this point, the agent application runs on the agent chip, and it does so completely independently of the kernel. It's just running on top of bare hardware, and it has access to I/O. And then here it can do its job. So for running a Bitcoin agent, for example, it can receive a transaction from the outside world, display it to the user, receive confirmation via a button press, sign the transaction, and send it back out. After the agent's done running, it has only one way of interacting with the kernel. So all it can do is terminate itself and optionally persist some state while it's doing so. So the agent can send back state to persist over the kernel, and then the kernel, on behalf of the agent, will save it to the persistent storage, after which it will terminate the agent. When the user wants to run another program, this whole process starts over, beginning with completely resetting the agent chip. With this architecture, Notary aims to achieve non-interference between two different agents that run one after another on the same piece of hardware. So suppose we have a scenario where we're running some agent A, and then we switch to running some agent B. What sorts of things might potentially go wrong here? What should we be concerned about? Well, one thing is that if agent B is malicious, it might try to steal secrets of A, which might be present in the hardware after A is done running. Non-interference says that A and B can't affect each other's behavior, so that rules out this scenario where B tries to steal A's secrets. Notary achieves non-interference by clearing state in a chip as the first step in launching any agent, and we call this process deterministic start, because it puts the chip in a deterministic state. And to see how this ensures non-interference, we can walk through an example. So consider a situation where a particular agent A is running on the agent chip. And consider two possible worlds, one where some secret bit inside the chip is 0, and another world where the secret bit is 1. You can think of the secret as A's private key or some other sensitive data belonging to A that shouldn't be exposed to other agents that might run on this device afterwards. When A is done running, the chip will be in some other state. And the state might be influenced by the value of the secret bit from earlier. So the secret could be explicitly present somewhere. Like for example, maybe A left the secret lying around in RAM. Or the secret could be implicitly present. For example, the microarchitectural state of the CPU might potentially be affected by computing over the secret data. Another possibility is that some peripheral inside the chip is affected by the secret bit. In any case, applying deterministic start to either of these states makes them converge to the same final state, setting all state inside the chip to some well-known value. And so clearing all the state in the chip ensures that the state, right before the next agent is launched, is independent of the secrets that might have been in the chip beforehand. So when agent B runs, its execution is completely independent of that of agent A. Now, zooming in on this deterministic start operation, how does this need to behave in order for this property of non-interference to always hold? Well, it needs to ensure that no matter the state of the chip, all internal state is cleared, that all bits inside the chip have some well-known value after this operation. And conceptually, you can think of this kind of like zeroing all the internal state. But there are a couple challenges in implementing this idea of deterministic start. One issue is that there's a lot of state inside the chip. Not only are there registers, which exist at the architectural level, but there's all this internal state, like microarchitectural CPU state, things like CPU caches, and there's a bunch of state outside the CPU but elsewhere in the system on a chip. So there's state in the RAM, and there might be stateful peripherals on the SoC as well, like the UART or SPI might maintain internal state. Another issue is that this operation of deterministic start has to work for all states. And what that means is that the chip might be in some malicious state set up by an adversarial agent, but still, this state clearing operation shouldn't be affected by this. And so how do we actually implement this idea of deterministic start? Unfortunately, simple approaches don't work. One of the most natural things to try might be just to assert the reset line on the chip. But this really only does the minimal thing necessary to get the device going again. So it does things like resetting the program counter, but not all that much else. So on our chip, for example, reset left some state lying around in registers, and it also left some state lying around in CPU internal caches, and also in the RAM and peripherals. So basically, state left over all over the place. A more aggressive approach we might consider is power cycling the chip. But this doesn't work either, because state in these chips can take minutes to decay. And that's why things like cold boot attacks work. And so what do we do? Well, Notary's approach to this problem is to use software to help. So we note that asserting the reset line, even though it doesn't do all that much, at least it returns control because it resets the program counter. And so our idea is to have software that lives in boot ROM that finishes the job of clearing internal state. But how do you actually write this code? It's a kind of weird thing that we're trying to do. We're used to thinking about code at the level of the abstract machine, but here we're trying to write code that has some effect on the internal state of a chip when the chip runs that code. And this code must clear every single bit of internal state in order for our non-interference property to hold. And so how do we actually write this code, and how do we know that we didn't miss any internal state while doing so? Our solution to this problem is a tool we built that analyzes the gate level description of the chip. So we realize that at the RTL level, there is no hidden state anymore. All digital state is explicit. And so what we do is we take the RTL implementation of the entire chip, including the CPU, the implementation of the CPU, the peripherals and the implementation of those, how everything inside the chip is wired up together, and also the boot code, which is it's part of the ROM, it's part of the description of the entire chip. So we take the whole chip and we convert it into an SMT-compatible format. And then from there, we have a tool that can check if the chip satisfies our deterministic start property. And it does this by simulating the circuit. But it's a little bit different than regular Verilog simulators because it simulates the circuit symbolically and can analyze what the circuit does from all possible starting states. And so what does it look like in practice to use this tool to build up and prove correct the reset code in our chip? Well, let's take a look at how we proved the code for the prototype that we built. So we can imagine starting out with no reset code. Like, think of this as leaving the contents of the ROM being all zeros. What happens if we take the RTL description of the chip with nothing in the boot ROM and see what our tool says? Well, it's probably not going to work, but we can try running our tool anyways. And what it says here is it says, error, state not cleared. And here it's pointing out a particular piece of state inside the implementation of the chip that the tool is not able to prove is always cleared correctly. And so here, it says that sock.cpu.latchedRead is not cleared. And as a programmer, what we do is we look at this and we consult the implementation of the CPU. So I go and look at the Verilog code for the CPU and go and find this latched read thing and try to figure out what it does and figure out how I can write some code that has just the right effect on this internal state. And so it turns out that this piece of state corresponds to something in the memory read machinery of this chip. And so I might realize that when this chip executes instructions, it's fetching instructions from memory. And in the process of doing so, it's going to end up clearing this internal state. And so I might actually start out my reset code with a bunch of no-ops. So this doesn't do all that much, but the process of reading this code from the memory actually ends up clearing that particular register that my tool complained about earlier. But this is still not enough, so I run the tool again, and it complains about something different this time. So now it's saying that sock.cpu.cpuregs1 is not cleared. Again, consulting the Verilog code, I might realize that this corresponds to architectural level registers, and so I could write some code that just sets all the registers to some well-known value. Running the code once more, I see it complains about some other piece of state, and this time it's some internal state, sock.cpu.memwdata. And then reading the code and understanding it, I'd realize that this register corresponds to something involved in the memory write machinery that doesn't get reset after the reset line's asserted. But it turns out that if I issue a dummy write, this register does get cleared. So here, storing this value to a read-only region of memory doesn't change the memory contents, but it does change the internal CPU state when it tries to execute this instruction. I run the tool again, it complains about something else. Turns out I didn't actually clear the RAM in this chip, but that's easy enough to do. I can just loop over RAM and set it all to some well-known value. I run the tool again, it complains about something else. Now it's saying that the UART's control register 0 doesn't get cleared after a reset, but it turns out that this thing is a memory mapped device, and then issuing a write to the right location ends up clearing this register that's inside the peripheral. And I run my tool one last time, and now it says, rather than error, deterministic start verified. And what does this mean? It means that the tool has proven that our chip, along with this reset code burned into its ROM, satisfies this property. So it means that if I take my chip and I assert the reset line, and then I let the chip go for some number of cycles, in this case, n equals about 180,000 cycles, which takes about 10 milliseconds in our chip, it means that no matter what the state was before the reset, afterwards, after 10 milliseconds, all the internal state in the chip will be cleared. And so our physical prototype of Notary uses that verified start code, along with the idea of the separation architecture. Our architecture requires some extra hardware compared to traditional hardware wallets. So existing wallets cost on the order of $100 to the consumer. Notary adds about $8 in hardware cost, so it's affordable. Notary's trusted computing base is about 4,000 lines of code, so this is for the kernel and related functionality. And most of this is for driver code. And then we have a bunch of applications that run on top of this platform. So we have two agents that we built, and pictured here is the Bitcoin agent. So on the left, we have a transaction being set up on the PC. So that's my laptop. I've set up a Bitcoin transaction. I'm trying to pay somebody. But I can't actually confirm the transaction on my computer because it doesn't have the private key. What I have to do is send this over to my device. And on the right, I have a picture of the device's screen. And then here, it's parsing the transaction and displaying it out to me. And I can either confirm or deny it. And only if I approve this transaction on the device and press the approve button does the device sign the transaction and send that back out. And then we have another agent that we built. So we have a general purpose transaction confirmation agent that works with web applications. So here it's being demonstrated with a DNS manager application. So on the left, we have the web app where we're trying to delete a domain. And on the right, it's requesting confirmation on the Notary device. So here we're trying to delete domain mit.edu, and I think we want to cancel this one. So we evaluated our prototype and found that Notary is practical. Unfortunately, I don't have time to go into the details of this, but in short, we found that Notary's design prevents bugs that have occurred in past hardware wallets while preserving the developer and user experience. And you can see the paper for a detailed evaluation. There's a long line of work in hardware security devices, both on hardware security devices and also on verifying security properties. So there's verified operating system kernels, and there's also work on verifying security properties of hardware. And you can see our paper for how these different things relate to Notary's design. To summarize, we contribute the Notary separation architecture, a new design for hardware wallets. Notary uses an idea we call reset-based switching to run agents one after another on the same physical chip while ensuring strong isolation between them by completely resetting this chip between running different agents. And this state clearing operation is formalized as deterministic start and proven correct for our prototype. And then we have a physical prototype along with applications that run on it, demonstrating that we can achieve functionality similar to existing hardware wallets while improving on security. For more information, you can see the link below, and I'm happy to take any questions.
So come closer to the mic so that you can hear.
Hi, Isaac Sheff, Max Planck Institute for Software Systems. I really enjoyed the talk, and I was wondering if you could clarify your threat model a little bit. So as a user on my smartphone, I don't want to just run the application, the agent application on my smartphone because I may not trust the phone. But at some point, I have to get that application onto the Notary device. So do I load the application code from my smartphone to the Notary device and then trust it once it's there? And if so, how did I trust my phone to send the Notary device the right application in the first place?
Yeah, so the question is, how do you actually get the application on the Notary device in the first place? That's a great question, and we didn't have time to talk about the entire flow of how the user interacts with the Notary, like end to end, in the 16-minute talk. In short, the answer is yes, there needs to be some good solution to that. And you either need to verify that you've downloaded the right application out of band, so like you can walk into your bank and they can tell you, oh, here's our public key. You can verify on your Notary device that the application you installed that came from the internet is indeed signed with that public key. Or there are a couple other approaches we propose that could be used. And there's more details in the paper about this.
Yeah, so Yun Hao from Cornell. So I have one of this hardware device, and actually it gives me a magic number, and the magic number refresh every 5 minutes. So it seems to me that the actual time matters here. So I'm wondering what is the role of actual clock input in this system?
Could you come a little closer to the mic? I couldn't
Oh,
hear.
sure.
Yeah.
I said that I have one of this device, and this device gives me a magic code when I wish to use it, and every 5 minutes, the magic code refreshes. So basically, I think that the actual time, the actual clock time, it matters as input for these applications. So I'm wondering what is the role of actual clock input in your system?
Okay, so is the question how devices like RSA Secure ID that provide one-time passwords, how does that relate to devices like hardware wallets? So the short answer to that question is that they solve slightly different problems. These one-time passcodes are really great when you want to protect against phishing attacks. So you're using your computer, you're about to log into the wrong website. Things like U2F or like one-time passcodes kind of help with that sort of scenario. Or one-time passcodes help with lost passwords. But hardware wallets protect you against an entirely different scenario where there's malware on your computer. If there's malware on your computer and you log in really securely using a one-time passcode or using U2F, right after you log in, the malware can do all sorts of bad stuff. And that's why we want transaction confirmation on a separate secure device.
Thank you.
Hi, Joel Niter from University of British Columbia. I'm questioning the applicability if you're not making your own hardware. There may be some hardware vendors that may not give you access to their RTL. How would you handle that case?
Yeah, that's a great observation that our approach depends on knowing the details of the hardware. So we really need access to the RTL. What we imagine is that this works great with open source hardware, like a lot of RISC-V chips. And we imagine that manufacturers, like say ARM doesn't want to release their RTL, well, they could go through the same process using our tool, build code that correctly resets their chip, and then just supply this as a binary. And they could promise, like, this does the right thing, we verified it, here, you can use it, you don't need to know the RTL.
Thanks.
Hi, Hassan Wasal from Google. So I wanted to understand, I understand this is an embedded processor, but are we going to be able to reset every bit of the chip something like branch predictor state. How can you reset that? Do you have any?
Could you try
thoughts?
speaking a little bit louder, please?
Okay. How can you reset something like branch predictor state?
That's a great question. So it's a good observation that we're working with really simple chips right now, and we're focused on formalizing this deterministic start property and proving it correct for the kind of chip we might want to use in this simple application. And it's future work to figure out if we can apply these techniques to much more complicated chips that have fancier internal state. But it's something we're working on.
Okay. Thank you.
Curtis Miller from CSIRO's Data 61. You said you had a kernel with 4,000 lines of trusted computing base. Do you have any means of verifying that that is actually trustworthy code?
Yeah, so that's a great question. Can we reason about our 4,000 lines of code and have a stronger guarantee that's correct? So it's currently part of the trusted computing base, but we believe that the way the code is written, it's amenable to formal verification, and in particular, push-button verification, as you'll see more tomorrow in the Serval talk. So we think that we can use verification approaches to prove the kernel code correct as well, but that was not done as part of this work.
So we're going to take the last question.
Hi, Chris Haster from ARM, and I was wondering about one small part, which was, it was interesting to see the tool that would find the initial state, but I was wondering why the tool wasn't connecting the loop, why the tool wasn't actually also generating the instructions to reset the state, if there was a reason for that.
So that's a great question. Why doesn't the tool just produce the code for you? I think it'd be neat to build a tool that can do such a thing, but I think it's kind of complicated. So our first step was building a tool that can, one, check that the code does the right thing, and two, kind of guide you in the right direction. It'd be really neat to figure out if we could synthesize this code, but I think that's a hard problem.
Thanks.
Okay, let's thank Anish once more.